NASA's Aeronautic Safety Program is a program designed to help pilots fly their planes safer, to know where storms are so they could fly around it, to be sure they know where other planes are so they won't crash with them, to understand where the ground is so they won't have difficult emergency landings. It'll help them maintain the planes better so they won't have engine problems, they won't have cracks in the wings, they won't have electronics that fail. It'll help them see through storms and see through the night, and it'll make airports much safer.
Hi, I'm Van Hughes for Connect. You know, it seems everybody is always talking about the weather. I mean, anyone can easily adapt to the change in weather conditions. There are many variables that help define weather, like the sun, the rain, and even the snow. But weather can also influence a lot of things in our everyday life. In this program, you will learn how weather impacts air transportation and the actions taken by pilots and ground operators in preparation for planes to fly during inclement weather conditions. You will see two examples of NASA and FAA research that is currently being conducted to address weather-related air travel concerns. For example, the F-106 behind me was subjected to lightning strikes by NASA researchers to study how lightning impacts airborne aircraft. That's pretty cool. In this program, you will be asked to participate in a math-based problem and experience firsthand a demonstration of how weather can impact air travel. At any time during this program when you hear this, and you see that on the screen, write down the Connect web address. By using an internet-accessible computer, you'll be able to access NASA and FAA researchers and hear from them their perspectives to questions presented throughout this program. You'll also find other experts highlighted, including meteorologists, pilots, and even kids like us. But for right now, join us as we begin a new season of Connect. The United States is subjected to some of the world's most diversified weather conditions. During the course of a normal year, our country may experience plus 100 degrees temperatures, jungle humidity, negative 30 degrees cold, severe drought conditions, as well as being the world leader in tornado activity, not to mention an occasional East Coast hurricane. As our transportation system has expanded, so too has our tendency to commute on a daily basis to work and recreational events. The potential for weather to complicate our lives is therefore also increased. Aviation, perhaps more than other readily available mode of transportation today, is strongly impacted by weather conditions. Did you know that 75% of all airport delays are related to weather? In 1996, the estimated price tag for weather-related delays, diversions, cancellations, and unexpected operating costs was $2.1 billion. The U.S. government invested approximately $830 million in aviation weather efforts during 1997. As the magnitude of these numbers indicate, ensuring weather-related safety and efficiency of flight has economic and human life ramifications to business and traveling public communities. Weather has a continual impact on both the safety of aircraft in flight and the efficiency of operations throughout the national airspace system. To complicate things even more, air traffic is projected to triple over the next 20 years. More planes and people in the air flying longer distances more often. Imagine what a weather delay will mean with more air traffic. Talk about a traffic jam. How important is weather information to your daily activities? How well do you understand the weather system and the interaction of the various elements on the daily forecast? But most of all, how might weather in one location affect your planned travel to a different region? Today's meteorologists have the tools and advanced technology to explain complex weather phenomena in a way that's simple to understand, thanks largely to satellite information and computer-based modeling. Dennis Smith of the Weather Channel in Atlanta, Georgia, has offered to explain and help us understand the fundamentals of weather. Dennis?
Thanks, Van. As many of you know, the Weather Channel provides 24-hour weather information both from a national and international perspective. Our meteorologists constantly monitor and update weather information. Now today we're going to fly through some basic weather concepts and talk a little bit about winter weather, which can cause some problems for aircraft. To explain how our weather occurs, we must first travel out past the boundaries of our atmosphere, 93 million miles away. Our sun emits visible and invisible energy that we call solar radiation. Radiation from the sun travels through the Earth's atmosphere, heating the air, the land, and the water it contacts. The Earth's surface absorbs much more radiation than the atmosphere. This means that the sun heats the ground and the ground heats the atmosphere. Not all parts of the Earth are warmed equally. Regions around the equator receive more concentrated solar radiation than do areas around the poles. The result is that the equator is warmer than the poles. Temperature differences also result because land and water do not absorb solar radiation equally. Because air moves, warm air and cold air are constantly mixing in the atmosphere. This mixing not only evens out the global temperature contrast, but results in the various weather conditions we see every day. If solar radiation penetrates all layers of the atmosphere, then why does nearly all weather occur in the lowest layer, the troposphere? The troposphere is warmest near the ground and cooler the higher you go. This temperature pattern is favorable for the development of vertical air currents. Relatively warm air tends to rise, and relatively cool air tends to sink. As warm air rises in the atmosphere, it expands and cools. As air cools, clouds can form, and precipitation can fall. Warm air rising causes less pressure to be exerted by the atmosphere, lower air pressure. Cool air falling causes more pressure to be exerted, high air pressure. As warm and cool air flow from one region to another, pressure changes, and so can the weather. When air pressure falls quickly, it usually means that stormy weather is approaching. That's the result of a low pressure system. When air pressure rises, fair weather typically results. That's the result of a high pressure system. Wind is another byproduct of changing air pressure. Winds flow because of the pressure differences in the atmosphere. Air moves from the areas of high pressure to areas of low pressure. Winds spiral inward toward low pressure, causing a piling up of air, forcing air to rise and cool, forming clouds and eventually precipitation. Around high pressure, winds spiral outward, promoting sinking air and fair weather. Okay, now, while you're soaking up that information, let's think of something a little bit more fun. Snow days. When you think of winter, is this the picture you see? Snow, snow, and more snow. But there are other types of winter precipitation. The type of precipitation that falls during winter depends on how warm air moves over a layer of below freezing air. A good place to start is with sleet. Sleet is frozen precipitation falling as ice pellets. These ice pellets form when snowflakes pass through a thin layer of warm air and melt. They refreeze into ice pellets as they fall through another layer of colder air close to the ground. Freezing rain is made of water droplets that fall to the Earth's surface and freeze upon contact with the ground or objects near the ground. For freezing rain to develop, cold air close to the ground needs to be shallow. The rain doesn't have time to freeze into ice pellets, but upon contact with frozen objects, it turns into ice. Snow is frozen precipitation in the form of a six-sided ice crystal. Snow is produced in clouds where water vapor changes directly into ice crystals that remain frozen as they fall to Earth. Snow will fall when temperatures remain below freezing from the clouds to the ground, or when a very shallow layer of above freezing air is present near the ground. Winter weather can be a lot of fun to play in, but it can cause some problems for us when we try to get out and travel, either by foot, by car, and especially by air. Now that you have a better understanding of weather, here's a question for you. Weather reports of snow are typically based on visibility. Snowfall is considered heavy when an observer cannot see very far through the flakes. But visibility is not the critical element for the meteorologist interested in aircraft operations. What do you suppose is the main issue that is considered in looking at snowfall from the perspective of aviation? Back to you, Van.
Thanks, Dennis. We have just seen the Weather Channel for people, but can you believe that airplanes need their own weather channel? To tell us more about the Aviation Weather Channel is Tom Van Meter of the Federal Aviation Administration.
Thanks, Van. Pilots need to have a continual awareness of the changing nature of the atmosphere on their route of flight in order to be able to react to changing weather conditions in a safe, efficient, and timely manner. It is the job of the weather coordinators here at the FAA's Air Traffic Control System Command Center to provide aviation weather information to operational aviation decision makers, such as traffic management and severe weather specialists here at the Command Center, along with the traffic management units and severe weather specialists in the field facilities. While the National Weather Service looks at a wide range of weather conditions, the information that the weather coordinators are looking for is aviation related, such as icing conditions and thunderstorms that can have a major impact on the national airspace system. Weather phenomena such as thunderstorms, clear air turbulence, volcanic ash, and severe icing can cause large portions of the national airspace system to be unusable. Geographical features and altitude also have an effect on aviation weather. Moisture drawn from the Great Lakes can cause lake-effect snowstorms to form on the east side of the Great Lakes, while the rest of the Midwest remains clear. When icing conditions such as freezing rain occur at an airport, ice may build up on aircraft wings, changing their shape and adding a considerable amount of weight to the aircraft. This change in shape and addition of weight can cause the aircraft to be unable to fly. To counter the effects of icing at certain airports, the airport may go into a de-icing status. De-icing is a slow procedure in which the entire aircraft is sprayed with a de-icing fluid to remove the ice and temporarily prevent additional buildup. Because of the time it takes to de-ice an aircraft, there is a reduction in the number of aircraft that can depart from that airport. When this happens, if a corresponding reduction in the arrival traffic is not made, the number of aircraft on the airport will grow until there is no longer any ramp space left in which to park additional aircraft. This situation is known as gridlock. The traffic management specialists at the Command Center monitor the situation at airports in a de-icing status, and if necessary will adjust the arrival flows in order to accommodate the airport's capacity and prevent it from going into gridlock. When icing conditions aloft impact a large geographical area, the traffic management specialists in the Command Center's Severe Weather Unit work with the affected facilities to develop routes around the icing conditions. Aircraft that are not equipped for flight into icing conditions may use these routes or may divert to another airport to wait until the icing conditions have passed. Aircraft that are equipped for flight into icing conditions may fly through the area if desired. Consider the weather-related condition of icing. Are icing characteristics the same everywhere? So let me ask you, how might geographic and atmospheric features contribute to icing differences in different regions of the United States? So now you know, people aren't the only ones that need a weather channel.
Consider the dilemma in working in the field of meteorology. Unlike other science fields where laboratory tests can be performed under tight controls, meteorology has no laboratory except for a vast dynamic atmosphere outside. Our friends at the Weather Channel and the FAA Air Traffic Systems Command Center have helped demonstrate the science and art in making weather predictions and decisions that affect us on the ground and in the air. Hi, I'm Shelley Canwright, Pre-College Officer for NASA and host for the Connect series. Thus far, we have been given some basic understanding of weather fundamentals and the impact weather has on aviation operations. Meteorological conditions, which have been frequent causes of aviation delays, injuries, and accidents, include poor visibility, thunderstorms, wind chill or microbursts, clear air turbulence, snowstorms, freezing rain, and icing. In today's program, you will hear from leaders in the federal government who have made aviation safety and aviation weather a specific mission. Central to this is research. It's a key factor in the development and implementation of new technologies related to aviation weather. And because of all that, you're going to have the opportunity to visit some unique NASA facilities and witness groundbreaking research. And as you listen to the researchers' stories on their investigations, consider these questions. What is the relationship between science and technology? What is the role of mathematics and mathematical tools in scientific inquiry? And what is the value of collaborations and partnerships in conducting research? We've already mentioned the many types of meteorological conditions that can affect aviation operations. For the remaining portion of this program, though, we're going to limit our focus on one type, icing. Icing can have a profound effect on both the in-flight and ground operations of aircraft. Let us visit two NASA research centers that are involved in various icing research studies. We'll start our icing travels by visiting NASA Lewis Research Center in Cleveland, Ohio, and its icing research tunnel. Now, this facility is the world's largest refrigerated wind tunnel. So bundle up. Let's go visit this giant cooler and have a closer look at icing effects on aircraft and the icing research being conducted. Listen to learn how one measures the effects of ice on aircraft performance.
Thanks, Shelley. My name is Dr. Judy Foss Van Zanti, and I'm standing in the test section of the icing research tunnel. Right now it's nice and warm in here, but later on it's going to get really cold. All right, what this tunnel was built for was to simulate down here on the ground what it's like for an airplane to fly through an icing cloud up there. We do this by creating a cloud that mimics what you see up there. As one of the research engineers, I asked the operators to select 5 parameters. One is the airspeed coming past the model. One is the temperature, how cold it is, always below freezing. 2 parameters are about the cloud density, how much water I have in the cloud, and also how big each drop size is. The final parameter I select is the time that I'll be flying through that cloud. I select the cloud conditions, I select the model, I either select an engine, which provides the airplane forward thrust, or I select a wing, which provides the plane lift, and I want to see one of 3 things. One is, what kind of ice do I grow on my model? What does it look like for the given cloud condition? Another thing I might want to look at is how to keep ice from growing on that, an ice protection system. And a third thing I might want to look at is to see how well I can predict what the ice shape is going to look like using a mathematical model and a computer. All these 3 functions are done in the tunnel. I use this tunnel along with Tom Rutvaski for the tailplane icing program. What we did there was to see how ice contamination affects the operation of the tailplane. Let's take a look at what the tailplane is and how it affects the aircraft operation. What we have here is an animation of an airplane in flight. The forces acting on this airplane are the weight, which acts through the center of gravity. The upward lift is provided by the wing, and the tailplane on the right side of the screen provides a downward lift. In equilibrium flight, we've got the following force and moment balances to consider. We've got the weight, which acts through the center of gravity, which is also the aircraft's pivot point. That's always forward of the wing center of lift. Those 2 forces acting together create a nose-down pitching moment. The tail comes in to provide a downward lift. As you can see, that's a simple geometry problem. The plane acts an awful lot like a seesaw. The tailplane icing project that Tom and I worked on investigated the question of what happens if you move that wing center of lift further back. How does that affect the tailplane if you've got an ice shape on it? We at NASA Lewis Research Center took this information and gave it to the pilots so they can make better and safer operating decisions. Back to you, Shelley.
Good science boils down to making as many high-quality observations as possible and then analyzing and interpreting them. At NASA Langley Research Center in Hampton, Virginia, a 5-year research program called the Joint Runway Friction Measurement Program is underway. This international effort is investigating aircraft losing traction on icy runways. This icing research program is having some groovy spin-offs. Let's meet with Tom Yeager and learn more about runaway runways.
Thanks, Shelley. I'm standing here this morning in our aircraft landing dynamics facility shop area. Behind me you can see one of our test carriages. We've got a display here of a landing gear system that we're looking at to evaluate from a standpoint of reducing the loads going into the fuselage. On my right here is a display showing some of the work that we've done to support the shuttle tire program that got started in the mid-70s and has been quite successful since then. We've done several modifications to the runway down there based on research data that we obtained here at our aircraft landing dynamics facility in Hampton, Virginia. We've also done work in modifying the tire design and the brake unit that's used on the shuttle that's being flown later on this month from Kennedy Space Center. We do a lot of work looking at aircraft tread design, how the grooves are positioned, and minimize the hydroplaning potential that can occur during aircraft landing and takeoff operations on wet runways. You're viewing a typical aircraft landing gear tire touching down on a contaminated or ice-covered surface. And due to the reduced friction capability between the tire and the ice, it takes a considerably long time for this tire to spin up to a speed that's equal to the forward motion of the airplane. We're currently involved in the 4th year of a 5-year program with partnership with the FAA, Transport Canada, the National Research Council up in Ottawa, the National Defense Department out of Winnipeg, as well as several aviation organizations supporting this activity, where we're evaluating aircraft braking performance under winter conditions. These conditions include snow, ice, slush, and water. And to date, the majority of the tests have been taking place in North Bay, Ontario, which is about 2.5 hours north of Toronto. We've evaluated braking performance of a Falcon 20, a de Havilland Dash 8 airplane, an FAA Boeing 727 airplane, and a NASA Boeing 737 airplane. Coming up in this program, you'll be involved in a classroom experiment that will give you a better idea of how the coefficient of friction influences the motion of two objects, for example, pavements and tires. In our work here at the track facility, we've identified the fact that the higher the friction coefficient, the shorter the stopping distance is for an airplane operating on a runway, and the less chance he has of going off either the side or the end of the runway. Some of the equations that determine this behavior of vehicles operating on pavement surfaces will be explained to you in the classroom experiment, and I want to wish all of you good luck in conducting that experiment.
Just seen the tip of the iceberg regarding the amazing researchers, and research tools. Makes me wonder, though, what other new technologies are under development for reducing icing hazards. But you know what? Now's the time to put you to work. Coming up is a high school student who has spent the summer at NASA Langley in a 9-week mentorship working closely with Tom Yeager. John has prepared a special hands-on, minds-on activity which a group of students will demonstrate. Following the program, you are encouraged to replicate the same investigation.
I spent 9 weeks in a NASA program for high school students called SHARP. Under this program, I had the opportunity to work with Mr. Yeager. I learned a great deal about the research being done on runway friction, tire designs, and new types of runway surfaces to minimize bad weather effects. I have to admit, I was a little nervous at the beginning just because I wasn't sure if I knew enough math and science to be able to grasp the research and to be able to help out in the evaluation of the research data. But I did okay. I found that the math I had taken in middle school and high school gave me a good foundation that I could build on. With the help of 2 undergraduate students that I worked with during the summer, Brian and Jonathan, I have a simple experiment that I would like you to try. In this experiment, you will investigate how surface conditions influence the coefficient of friction between 2 surfaces. Your surfaces will include a ruler, sandpaper, and objects found in the classroom. Now, my friends and I did an experiment similar to the one you're about to do, but it was a little more complicated and involved a little more math. This experiment has been recreated on the Connect Plain Weather website, so you might try this with your friends or your family following the program. Enough said. Let's get started. The math formula you will need in doing your experiment looks like this. Friction coefficient equals height divided by length.
The following materials were collected for our experiment. 3 metric rulers, at least one of the rulers had to be plastic, a sheet of sandpaper large enough to cover a ruler, and 4 objects to test: a rubber eraser, a large metal paper clip, a plastic film canister top, and a small dice. John helped us identify the dependent and independent variables for our experiment. The independent variable, which is what we would be changing, is the ruler surface. We used a plastic ruler to simulate a smooth runway surface, and then a ruler covered with sandpaper to simulate a rough runway surface. The dependent variable for the experiment was the classroom object. Before doing our test, we talked about how each object was alike and different. We shared ideas on how the surface condition, which we would slide these objects across, might affect the friction force of each object. We hypothesized about the effect the surface change would have on the objects. Here are our test procedures we followed. 1 metric ruler we identified as the test base and labeled with the number 1. It would be used to measure the length. A second ruler labeled with a 2 was held upright for the test. We would measure the height from this ruler. The third ruler labeled with a 3 was plastic and would represent the runway. One person handled the runway ruler, one person held the height ruler, a third person was responsible for reading the height and base measurements, and the fourth person was responsible for recording data. In running our 2 surface tests, we were interested in collecting the height measurement for the vertical ruler and the length measurement from the base ruler at the point when an object began to slide down the runway ruler. We tested each object 3 times on both a smooth and rough surface. The smooth surface was the back side of our plastic ruler. The rough surface was sandpaper attached to the ruler. Here is a diagram to show you how the experiment worked. Each test object was placed at the end of a ruler, and then one end of the ruler was slowly raised. We stopped raising the ruler when the object started to slide down the slope of the runway, and then took our measurements of height and length. Now that we have finished our testing, we are ready to look closely at our data. First, we will calculate the height and length average for each object on each of the surface types. Using these averages, we will apply John's formula to find the friction coefficient. That formula is friction coefficient equals height divided by length. Now we are ready to answer our question. What effect does surface condition have on the friction coefficient between 2 surfaces? Well, this is our experiment, and we leave you with a challenge. What other variables can you think of to test in this experiment?
Okay, gang, you've received your challenge. Complete your own runway traction experiment and then do further tests on different surface conditions. As we bring this program to a close, let me remind you to check out the Connect website for responses from a variety of experts to questions posted throughout this program, and also to participate in an online friction experiment. Let me slide things to Van now for some closing comments. This is Shelley Canwright for Connect, connecting you with real science and with real scientists in near real time. Take it away, Van.
Thanks, Shelley. I hope you all have a plain understanding of plain weather. I know I sure do. Join us for other Connect programs. Simply access our Connect website for our information and program availability. So until next time, stay connected.